Let's look at the raw physical power of rotating water. When a large mass of fluid spins around a central axis, it generates forces that dictate the physics of everything from bathtub whirlpools to weather systems. This diagram contrasts standard linear flow with vortex flow. In a linear stream, particles move parallel, but introduce rotation and interactions shift completely. Every vortex is defined by two parameters: tangential velocity and exact radial distance from the central axis. To solve any vortex problem on a fluid mechanics exam, your very first step is identifying the exact mathematical relationship between that velocity and that radius. Every rotating fluid experiences two distinct pressure gradients, acting at 90-degree angles to each other. This formula architecture shows pressure variation in rotating fluids, dictated by two competing terms. First, centrifugal force pushes fluid outward, creating a positive radial pressure gradient. Second, gravity acts downward, creating a negative vertical pressure gradient, governed by hydrostatics. How these two gradients behave inside a specific system depends entirely on one physical condition, whether or not a mechanical external torque is driving the rotation. Look closely at this mechanical impeller rapidly stirring a vat of thick liquid. This is a forced vortex. The rotation is sustained entirely because an external torque is continuously pumping energy into the system, forcing the entire mass of liquid to rotate as a single solid body. This solid body rotation diagram maps out the resulting velocity profile. Notice how the length of the arrows changes as you move away from the center. Because the angular velocity, omega, remains constant throughout the entire mass, the tangential velocity increases linearly as you move outward. The formula is simply v equals omega multiplied by r. This creates a massive trap for exam takers. Because an external mechanism is actively adding energy to the fluid, Bernoulli's equation is strictly invalid across streamlines. The total energy varies depending on which streamline you analyze. We can see how this continuous energy shapes the geometry by deriving the equation of the free surface, shown in this step-by-step logic panel. We start by setting the boundary condition at the free surface, where the pressure equals the constant atmosphere. When we substitute our forced vortex velocity, omega times r, into the general pressure equation and integrate it, the math resolves cleanly. We get z equals omega squared r squared over 2g. Because elevation z is proportional to the square of the radius, the continuous addition of external energy forces the surface into a mathematically perfect paraboloid. Now contrast that with water draining naturally down a sinkhole. This is a free vortex. There is zero external torque. The system is driven entirely by the conservation of the fluid's own existing angular momentum. Look at the velocity profile for this conservation of angular momentum. It is the exact opposite of the forced model. Here, as the radius increases, the velocity shrinks hyperbolically. The governing mathematical law is v times r equals a constant. Because no mechanical energy is added and the flow is inherently irrotational, Bernoulli's equation is perfectly valid. You can equate the total energy across any 2 points in the entire fluid mass. But plotting this creates a problem. This chart graphs the pressure variation when we substitute our free vortex velocity into the general pressure equation. We see a drastic pressure drop toward the center. If velocity is a constant divided by the radius, then as that radius approaches zero, the math dictates an infinite velocity. Infinite velocity is physically impossible. Free vortex equations are highly accurate for outer regions, but mechanically break down at the absolute core. But nature gracefully resolves this mathematical impossibility every single time a powerful tornado touches down. This graph shows the Rankine vortex. It is the mathematical model that accurately describes a real-world tornado by combining both flow regimes. At the dead center of the storm, extreme viscous friction locks the fluid particles together. This central eye acts as a solid body forced vortex, giving us that linear ascending slope. But outside that frictional core, the destructive winds operate free of mechanical constraints. This outer region behaves as an irrotational free vortex, following the hyperbolic curve. Complex natural systems are rarely pure mathematical models. They're layered combinations of basic forced and free boundary conditions interacting with each other. This quick recall sheet condenses the vortex taxonomy. Rapid identification of these velocity relationships and surface equations is required for exam calculations. Notice the geometry shortcuts. Knowing a paraboloid's volume is exactly half its circumscribing cylinder saves crucial minutes. Let's look at ESE question 8.2, where a free vortex transitions into a forced vortex at a critical radius. The execution relies on finding that interface. At the boundary, free vortex velocity perfectly matches forced vortex velocity. Equating both profiles gives the solution. Identifying the specific radius where flow regimes interface provides the mathematical bridge needed to solve for any unknown in the system. We can apply this Rankine model directly to question 8.5, which asks us to find the wind velocity of a tornado at an 80-meter radius, given a 50-meter-per-second velocity at the 40-meter edge of the eye. Asking for a velocity outside the central eye puts us in the irrotational free vortex region. Applying conservation of angular momentum, initial velocity times radius equals final velocity times radius. 50 times 40 equals v nu times 80. The new velocity is 25 meters per second. The math behaves differently because the energy sources are different. One system requires continuous mechanical input to maintain its rotation, while the other relies entirely on existing momentum moving through a gradient. Solving vortex motion is an exercise in energy accounting. Track whether an external torque is present, apply the correct velocity profile, and the fluid's geometry will mathematically reveal itself.